these fancy big name physicists on YouTube can help me out. It should be easy. Now, I hate to stick my neck out all the time, but I have questions about the relativistic explanation for magnetism, which we've all heard so many times before. And it's explained over and over on YouTube. I'll explain it one more time. But now let me just say, you other explainers, I've heard it explained quite badly and quite well. But please refrain from talking about positive charges moving in N-type materials. It never happens. And by the way, people in the industry, people who work with electronics, never talk about conventional current flow. There is no such thing. When we say current flow, we mean electron flow. And we always mean electron flow, except in a p-type material. So, you know, analogies get you in trouble really quick because they're analogies. So, they break down. You have two pieces of wire, two conductors, and you put current through them both. Put electrons through them both. That's what I mean. I always mean electrons. Unless I mean holes, and I will specify that. We have current going the same direction through the two conductors, and they attract because if you are an observer on one electron, you would see Lorentz contraction. You think that more positive charges in the other wire were closer together. And so it's positive, you're negative, and it attracts. That is the theory, and all the other interactions follow from that. Like Lorentz force, and you name it, it all follows from that. Now, we know that these electrons don't go any fraction, appreciable fraction of the speed of light through these wires, because they have lots and lots of electrons. Let's say this is a piece of wire. Here's my piece of wire. And you have lots and lots of electrons here. So really what happens is they drift quite slowly, but they say, well, there's equivalence between a whole bunch of them going slowly and one going very fast. So that's what I came to test. And I decided to take a quick look back at the equation for Lorentz contraction. And it is this. I'm going to take my camera off of there. And it is this. L length equals the length if it were going the same speed as u, that's L0. I noticed if there wasn't this c squared at the bottom, then, well, the square root of a square, it'd be kind of linear. But it's not. So it led me to a question. What if I have, here are my two conductors again, but here are two thinner conductors. Now surely the thinner conductors would have to have the electrons drift twice as fast to get the same current. So we have I over, well, in this case, I have a I over the cross-sectional area of the wire, and that gives us, I said V2 in this case, and over the smaller wire gives us V1. And of course, that's V1 and V2 are going to be in 2-to-1 ratio because the cross-sectional areas are too. So that gives me, using the old phone for the calculator and all that stuff, that gives me, for 1/4 the speed of light. Now, I'm not saying it goes 1/4 the speed of light or 1/2 the speed of light. I just picked some values. So here we go. For 1/4 the speed of light, that would give you a contraction. I had to pick numbers which would give me an appreciable contraction. That gives us 96.82 centimeters. And this bottom one gives us that. So these are the contractions for the two wires. Now, putting, I want to work with 1 meter. So I have to, here. So that would give us for a whole meter, I just put 1 over it. Sometimes I skip steps on my explanations, sorry, but you know what I'm talking about. So for 1 meter, length 1, I put 1 over length 1 and 1 over length 2 to get the values for 1 meter. And this is what I got. And now, these don't look right for 2 to 1. You see, I can neglect this 1 over here because these represent neutrality. We have 1 positive charge on the bottom and 1 on the top. That is to say that 1 that I just erased with my finger represents neutrality. That's if it were just 1 meter to 1 meter, it would be neutral. So this is the leftover. And you notice this leftover here is not 2 to 1 with the first. I would expect 0.07. I'd be happy with 0.07 or 0.08 or something like that, but this does not look good. So it looks to me like there is no equivalence between I1 and I2. Or that I1 and I2 are the same. I1 and I2 per square centimeter. And that means V1 and V2. They're quite proportional. But by the time I put it through this, the proportionality is gone. And so they are no longer equivalent. So, now, I don't claim to be great at anything except love and music. And I run into my problems sometimes and need a little help. And so I know that some able physicist could easily explain this to me, but I have another problem. We have all seen this. This is a photon, and it's got the E field going this way, and it's got it's got a magnetic field going this way, and they are at right angles to each other, and well, that's great. But here we have an electric field, and here a magnetic field, but we don't have any electrons. We don't have any particles. So how do we have a magnetic field if magnetism is only electrostatic force? That is a question. Now, maybe we don't really have one. I've never seen one. You can't measure it. But then there's Maxwell. And he was able to predict the speed of light using, to 4 decimal places, using permeability and permittivity. And permittivity is for the E field, and permeability is for magnetic field. And although they are, well, I have another problem there too. Now, you notice there are, I'll get to that in a minute, there are no electrons here to be relative to. There's nothing, a relativistic explanation doesn't work here because there is no, to have relativity problems, you have to have 2 parties moving it relative to each other. We have one party moving relative to itself. That doesn't help. So Well, it doesn't have a magnetic field. It appears to have a magnetic field because Maxwell. Now, I want to point out, just as an aside, that Lorentz knew about the Lorentz force. And he also knew about Lorentz contraction. And he did not attribute the Lorentz force to Lorentz contraction. Maybe he simply overlooked it. I don't think he was very sloppy. But it may have never occurred to him, and it may be true nonetheless. But it doesn't help with this. It does not help explain the wave motion of light. So, in fact, it doesn't help. It does not help explain light at all, because where's that magnetic field from again? Since there's no relative motion going on here. Yes, and I have one more complaint. Well, it's just something I noticed. Let me just note that permittivity and permeability feel very different. You know, I work with them all the time. We all do. That is, whether we know it or not. Permittivity is the resistance to an electric field of free space, or whatever the permittivity is of. In this case, free space. So, permittivity vanishes very quickly. It diminishes by 10 to the 11th per meter. And you'll notice that if you want to get any capacitive effect, you have to put the plates very close and all that stuff. Really, in practical terms, if you want to get noticeable repulsion out of an electric field, you've got to be within a millimeter. It drops off so quickly. A magnetic field, however, you know the working, for your average magnet, the working distance is more like in the inches, in the centimeters. So, not only that, well, and then for very strong magnetic fields, well, for very strong electric fields, you might expect an inch or two. I've had like 30,000 volts, and I can move a piece of wire that is, you know, gently suspended. I notice the attraction on a piece of wire at about a ½ inch. If I have a very strong magnetic field, well, it's in feet or meters. So, I don't know, you know, they're very different measurements, because permeability, all the lines connect back. That's magnetic fields for you. And in permittivity, all the lines radiate out from the charged surface. So they're very different, and it's hard to draw an equivalence for them. But from working with them, I can tell you that one appears to have a longer range than the other, and that doesn't sit right if they are indeed the same thing. Now, that might be a minor complaint. I think the wave example is a much more major complaint. And as far as the Lorentz contraction, I'm probably making a mistake. But don't just tell me that. Show me. Take me through your calculations. You know, this should be very easy for some. We have these name physicists who are doing these videos out there all the time. Have you ever seen them do an experiment? Well, maybe they do. We don't know what they do. But we know what they don't do. And what they don't do is help somebody like me, who they really don't need. A professor doesn't need a nobody challenging what they teach. But I have problems. And these pretty tough criticism. So I'm sure that some apt physics student could straighten me out on those calculations. Be my guest. Please do. Now, if some of you are students out there, and especially my overseas viewers, tell your professors, please. I have had this explanation from so many professors, well, only a few actually, you know, many more on the internet, of course, and no one has brought this up. Now, if indeed there is a good explanation for the apparent non-equivalence of two different sizes of wire, why was it never mentioned? Why is it never explained in any physics class? So please start. Now, another thing to note. Different sizes of wire do not have any effect on inductance, on magnetic force, but you would expect them to if the calculations, if there is not an equivalence in current A moving at velocity v and current 2A moving at 1/2 velocity v. So we have to address this. I do not have an alternative explanation for magnetism. Now, Feynman didn't live that long, but I surely would have spoken to him if he had, because I was not that far from Caltech in '93. He was already dead. But at the time, I did not have this particular complaint. And I have a video on Faraday's paradox. I hope you look at it.